Good evening. Before we come on to our main theme, I think everyone's anxious to know of the latest news about the Hubble Space Telescope, where there are faults, as we know. Professor Michael Disney of University College Cardiff is just back from a special Space Telescope conference in Baltimore, and he's very kindly come along to give us the latest news. Mike, first of all, what went wrong?
Well, as far as we can judge, about 10 years ago when the mirror was being ground and polished, somebody did something fairly drastically wrong, like setting a switch wrong or putting a lens round the wrong way, and the result is that the main mirror now is the whole of the area of it's not at the same focus.
How serious is it?
If we couldn't visit the telescope over the next few years, in other words, if it wasn't in shuttle orbit, it would be very serious because it would have meant we'd lost something like at least 80% of the capacity of the instrument overall. But because we can actually visit it and we can make corrections to the instruments and so on to compensate for this, it's not a disaster, okay? It's certainly not a disaster. It's still a telescope that can do things which no other telescope can do and which are exciting. But of course it'll do less of them in the first 3 years until it's visited again, and in what it does, it'll do more slowly.
What's the long-term outlook?
I think the long-term outlook's very good. I mean, we know in principle how we can correct most of the problems, how we can compensate for most of the problems. And so the real problem is one of delay for the most part. There are one or two things we can't do at the moment. We don't know how we could do them. But for the most part, we think we can recover the science over the full 15-year span of the project.
So people have been saying that the telescope is a failure. Well, this is, in fact, is quite wrong.
Yes, I think it's to say that it's a failure mechanically is true, but to say that it's a failure scientifically, judged over the term of the whole project, is completely incorrect.
It will, in fact, do things that no ground-based telescope can do.
It will, Patrick, definitely will do that. And there's quite a lot of exciting things that we didn't think we could do immediately after the disaster that was discovered, which we think we may be able to do in a few months. We're all busy on our computers now trying to unscramble these images, okay? It's called deconvolution, technically. Nobody's done this with data quite like this because it's unique data. It's photon noise limited and it is diffraction limited. And so actually I think that's an optimistic sign. We may be able to do things which nobody thought could be done.
Well, I think that's very encouraging. I know that everybody, everywhere, is going to wish you and the team the very best of luck.
Thank you.
Mike, thank you very much indeed. When I came on the sky at night last month, I referred to the total solar eclipse of this month, where the track crossed Finland. Well, that in the end is where I was, and I'm afraid that I was clouded out. It's my 7th total eclipse and my first failure, but the cloud was dense all over Finland. But nevertheless, a Finnish party did get some results from an aircraft flying at 40,000 feet, and they very kindly let us have them. So this is what the eclipse looked like from its vantage point. Here, first of all, is the partial eclipse, the moon advancing across the face of the sun. Now it's almost total. And now it is total, and the moon's right in front of the sun. You can see the sun's atmosphere, the pearly corona, which is fairly symmetrical because the sun is now near the peak of its 11-year cycle of activity. And there to the left, you can see the prominences, the masses of red hydrogen gas rising from the sun's surface, which you can only see with the naked eye during a total eclipse. Now the eclipse is almost over. The sun will start to emerge from behind the moon, and the very first segment is the Carnegie diamond ring effect. And there it is. And now the eclipse is over. Well, sadly, I saw nothing of that, but please don't be disheartened. You will see a total eclipse from England if you don't mind waiting until the 11th of August, 1999, when the track will cross Cornwall, and I can assure you that the sky at night will be there. And now, on to our main theme. After dark, look low in the south, and there you will see the planet Saturn. With the naked eye, it appears as nothing more than a fairly bright, slightly yellowish star, and on that picture, it's rather to the right of center. But as soon as you use a telescope, Saturn shows itself to be the gem of the sky, and you see that magnificent ring system that is unlike anything else in the solar system. And that black rim line going round the ring system is the gap between the main rings, known as Cassini's division. Now, Saturn is quite easy to find. I don't think you'll have any difficulty. It is, unfortunately, very low down. It's in the south, in the constellation of Sagittarius the Archer. And because it is at opposition this month, it's pretty well due south at midnight GMT. And there it is. Sagittarius itself, I may say, is not a constellation with any particularly distinctive shape. Some people liken it to a teapot, although I never understood why. But it does contain a very rich part of the Milky Way. And those lovely star clouds in Sagittarius hide our view of that mysterious region, the center of the galaxy. But at the moment, Saturn is very much the brightest thing in that part of the sky. And it's bright because it is large, even though, at the moment, it's 837 million miles away from us. But it's a big world, over 70,000 miles in diameter, but made up in a way very different from that of the Earth. We believe that there is, in fact, a rocky core at a fairly high temperature, surrounded by layers of liquid hydrogen. First of all, metallic hydrogen, and then molecular hydrogen. And above that comes the cloudy atmosphere, rich in hydrogen and helium, and the clouds we can actually see. There is a magnetic field, and there are radiation zones, but they're nothing like as powerful as Jupiter's. Well, I would like to show you here a drawing I made myself only a few nights ago with my own 15-inch reflector. And that shows the ring system, I think, reasonably well. You can see the division there, with a belt across the disk. But, of course, from Earth, that's about all you can get. And our first really detailed views were obtained by the Voyager probes in 1980 and 1981. And they really were amazing. There's a Voyager picture. Already you can see there the ring structure. And just look at this picture, showing the amazingly complex rings with thousands of narrow ringlets and minor divisions. We never dreamt the rings were like that, and we're not quite sure now why they are. But it may well be that Saturn's satellites, or moons, have something to do with it. There are, in fact, 17 moons. Most of them are small, cratered, and icy, as the Voyagers have told us. But there's one which is very interesting indeed, Titan. And Titan is bright enough to be seen with a small telescope. And if you have got a telescope, this is where Titan is going to be relative to Saturn during August. And it's not hard to see at all. In fact, I believe one or two people can see it with binoculars, even though I've never been able to do so myself. But it's quite large. It's about 3,000 miles across, very similar in size to the planet Mercury, and it does have a dense atmosphere, the only planetary satellite to do so. And so when the Voyagers went by, all they could do was to photograph the top part of a layer of what is virtually orange smog. Not quite uniform, as you can see there, but certainly no detail. And what, therefore, lies underneath those orange clouds? Well, the Voyagers couldn't tell us. We'd very much like to know. And for that reason, a new and very exciting space probe is being planned for the 1990s. Dr. John Zarnecki of Kent University is closely associated with this probe, and we are delighted to welcome him down to the sky at night for the first time, but I certainly hope not the last. Welcome, John.
Thank you.
First of all, what did we know about Titan before Voyager went by?
Well, it was discovered telescopically in the middle of the 17th century, but for the next 300 years, very little was learnt about it, until the 1940s, when a detailed study of its spectrum showed the characteristic signature of methane gas. Mm-hmm. So this implied the existence of an atmosphere. But other than that fact, the existence of an atmosphere and an approximate idea of its size, not a great deal was known about it until the advent of the Voyager missions.
Well, of course, there were two Voyagers, as we know. Voyager 2 went on to make those superb views of Uranus and Neptune. But in fact, Voyager 2 didn't image a Titan, because Voyager 1 had already done so. And if Voyager 2 had bothered about Titan, it would have missed out on Uranus and Neptune. So most of what we know about Titan is derived not from Voyager 2, but from Voyager 1. And what did Voyager 1 tell us about Titan?
Well, I suppose that compared with some of the truly remarkable vistas that Voyager revealed for us in some of its visits, the images from Titan were relatively unspectacular. As you have said, we saw a cloud-covered body. We saw many images showing only a little bit of structure in the cloud. Some images showed, in fact, a dark collar around the North Pole, as we can see, but relatively little was learnt from the imaging system. However, it was very different with some of the other instruments on Voyager, and as so often happens in astronomy, it's by studying the spectrum emitted by an object that we learn a good deal about it. And it's certainly true in the case of Titan that the ultraviolet and infrared spectrometers on Voyager really unlocked some of the secrets of the composition of the atmosphere.
What's the atmosphere like?
Well, I think the first thing to appreciate is that it really is very, very substantial. The surface pressure on Titan is some 60% higher than it is here on Earth. But even that doesn't give a true feeling for the extent of the atmosphere. We could imagine doing a little experiment. If I were to hold out my hand like this here on the surface of the Earth, I could in principle measure the quantity of gas in a column from my hand to the very top of the atmosphere. Now imagine doing the same experiment on the surface of Titan. If we compare the masses of gas, the quantity of gas in two cases, we find that on Titan there's 10 times more gas than in the comparable case on Earth. So it's a very substantial atmosphere. What about its composition? Well, one of the big surprises from the Voyager measurements was that it was not methane that dominated the atmosphere, but nitrogen. In fact, nitrogen makes up some 90% of the atmosphere. Methane then comes in a poor second, and hydrogen molecules make up maybe less than 1% of the total atmosphere. But in addition, Voyager found maybe a dozen other hydrocarbon gases, very low abundance, but definitely there. And this has caused a great deal of interest because it seems that the atmosphere of Titan is a very, very rich laboratory for a whole range of chemical reactions.
But of course, so far, we've only been able to study the top part of it. We still don't know what the surface is like, except that it's very, very cold. And that's the reason for sending up this new probe, the one we call Cassini. Now, why Cassini?
Well, it seems to be the fashion these days, particularly with planetary missions, to name them after an eminent scientist, artist, or scholar from the past. And in the case of a mission to the Saturnian system, well, the obvious choice seems to be Jean Cassini, who discovered 4 of Saturn's satellites, but is probably most well known for his study of the rings and for naming the gap in the rings the Cassini division.
Well, when's the probe due to be launched?
Current plan calls for a launch in April 1996. There is, in fact, a 10-day launch slot, only a 10-day launch slot in 1996. If that is missed, then it slips for something like a year. It transpires that 1996 launch window is the most favourable for the next 20 years. So there is a lot of pressure, really, already to meet that particular launch slot.
Particularly since the trajectory is going to be rather complex. You can't go straight from the Earth to Saturn. And in fact, it's going to be quite a business.
That's right, and that's rather exciting, and in fact it gives us a lot of opportunities to do more science on the way. Let me just quickly run through the trajectory that will take us to the Saturnian system. Assuming we launch in April 1996, then the initial orbit takes us out to the asteroid belt, and that opportunity is going to be taken to arrange a close flyby of an asteroid. In this case, the chosen target is the asteroid Maya, with a radius of something like 80 kilometers. So that'll occur about a year after launch. After that, we come back to the vicinity of the Earth and use the Earth's gravitational field to give us extra energy to sling us off to the orbit of Jupiter. And in going to Jupiter, we pass through the asteroid belt for a second time, and there's a possibility of maybe a second asteroid flyby. Once at Jupiter, we again use the gravitational field of Jupiter to give us more energy, and that enables the probe to reach the orbit of Saturn. And of course, also gives us the opportunity for, hopefully, some very important observations and measurements in the region of Jupiter.
Is Titan the prime target?
There are, in fact, 2 prime targets for this mission, and the way that is achieved is by actually having 2 separate vehicles. One is the so-called orbiter, provided by the United States through NASA, and the other is the Titan probe, provided by ESA, the European Space Agency. And these will be essentially locked together for their 6.5-year passage to the Saturnian system, but once they arrive there, their fates will be very different indeed.
What actually happens on arrival at Saturn?
On arrival, the Cassini probe is captured by the gravitational field of Saturn, and it enters an initial orbit which has a period of something like 4 months. And it's arranged so that some 3 months into that orbit, it reaches Titan. And a short while, some 12 days before arrival there, the two vehicles, the orbiter and the probe, are separated to go on their separate way.
What happens to the orbiter?
Well, after separating from the probe, it undergoes a small maneuver to deflect it away from Titan, and it then embarks on what is called a Saturnian tour. This is a large number of orbits, some 60, hopefully, of the Saturnian system. And as you can see, these orbits are very different, one from the other, and it gives us many opportunities to achieve the prime scientific objectives of the orbiter. There are really 5 main scientific objectives for the orbiter. Those are to study Saturn itself, to study Titan, because each orbit should take us fairly close to Titan itself. There is the ring system, of course, and this will be a marvellous opportunity for a long-term study with a fairly long time baseline to study the ring system, the magnetosphere of Saturn, and of course the icy satellites, because these varied orbits will enable us to fly past many of the icy satellites at different flyby distances, and it's hoped that in fact some of the best images will have a resolution. They'll be able to image details perhaps as small as 100 meters in the best case.
Well, that's going to be exciting indeed, but I think even more so the Titan lander. Will you tell us about that, John?
Yes, indeed. I should tell you that it's already been christened, in fact. It's called the Huygens probe, named after the Dutch physicist Christian Huygens, who discovered Titan. Now, after separating from the orbiter, which has essentially carried it all the way to Titan, this happened some 12 days before arrival at Titan itself, then the probe will be configured, it will be set up for its final arrival at Titan. It then hits the top of Titan's atmosphere at a very high speed, some 6 kilometers per second. And it's then that the very unaerodynamic shape of the probe comes into play. It's designed to be as unaerodynamic as possible so that when it hits the atmosphere, the friction against the top layers of the atmosphere will slow the probe down. And that will in fact bring the speed down to something like 0.5 kilometer a second. When that has happened, the outer decelerator, the ring which provides the slowing down, is jettisoned, a parachute is released, and that then slows the probe down further and allows the probe to drift down slowly through the atmosphere, taking some 3 hours to do so. And it's during that descent through the atmosphere that most of the instruments on board the probe will be doing their main task. There are really 2 types of atmospheric instrument. One type which will look at the radiation emitted by the atmosphere, and another type that will essentially take samples of the gas of the atmosphere and make direct measurements on the atmosphere.
And then, of course, comes the landing itself. And I wonder, what is the surface of Titan like?
Absolutely, and that is surely one of the most fascinating questions to be addressed by the whole mission. Now, there's been a lot of interest in the nature of the surface of Titan, particularly over the last 10 years since Voyager gave us a lot of information about Titan. The interest really stems from the fact that we really might be dealing with here a liquid-covered surface.
But not water?
Not water, no indeed. Let me explain why it's thought that it might be a liquid-covered surface. Now, we know that methane exists in the atmosphere. Voyager has told us that. We also have fairly good evidence, both direct and indirect, that the methane molecules in the atmosphere are actually being broken down by the effect of light through photochemical reactions. And this is an irreversible process. That means that methane is being lost. Now, the fact that we see methane at all implies that it must be being replenished. There must be a source of methane to replenish what is lost. If we assume that that reservoir, that source of methane is at the atmosphere, is at the surface, we know pretty well what the temperature and the pressure conditions are at the surface. If we then take this reservoir and put it at that temperature, we find that, lo and behold, it should be a liquid. You can see here that for a temperature of about 170 degrees, methane at that temperature and pressure exists as a liquid. But it's fairly close to what is called the triple point, the point at which methane could exist as a solid or as a gas. So it's a slightly uncertain prediction. But I think there's a lot of support for the belief that if the surface isn't entirely covered with oceans, we at least will have lakes, if you like, of methane.
A chilly methane ocean, I wonder. Could there be any waves in it, for example?
That's an interesting prospect. People have looked to see what this ocean might look like, how it might behave. And one of the interesting facts is that with the relatively low surface gravity, some 15% of Earth's surface gravity, waves driven by wind will build up very, very easily. So we might have really quite large waves driven on the surface of Titan.
Another point, John. When the lander gets there, how long is it going to last? I mean, how long is it going to be able to transmit before it goes silent permanently?
That's a tantalizing question, and of course we hope as long as possible. Technically speaking, the end of the Huygens probe mission occurs when the radio signal, the radio link between the probe and the orbiter, which is relaying the information back to Earth, is lost. We're told by the European Space Agency that the minimum time for that to occur is 2 minutes after landing. Now that's obviously quite a short time, but it's still possible to do a very great deal of measurements and of science in that time. We're hoping, of course, for a lot longer. There are, of course, other ways in which the probe could be killed. We know that the surface is very cold, and that might finish the mission. Or, of course, if it is a liquid-covered surface, we must ensure that the probe doesn't sink.
And the orbiter will go on operating for much longer.
That's right. That's operating, of course, in a relatively benign environment compared with the surface of Titan, and we hope to see at least 60 orbits, perhaps, spanning a time of 4 years. And throughout that time, we'll be receiving a continuous stream of data from the orbiter.
All in all, this is one of the most ambitious vehicles ever planned. What do you think of the chances of success?
Well, of course, we must be optimistic. You would never embark on a mission like this if one wasn't optimistic, and I expect that we might be sitting here in 13 years' time discussing the results from the Cassini mission.
And we will certainly do that. John, thank you very much indeed. So, if you get the chance, do take a telescope and go and look at Saturn. You would see it there, low in the south, not very far above the horizon, shining like a fairly bright star. And if you do have a telescope, you'll see the rings, and you should also see the star-like point that marks Titan. One of the most curious, baffling, and mysterious worlds in the entire solar system, unlike any other we know. Well, at the moment, Titan is very much of a puzzle, but we should know more about it by the year 2002, and I think we're in for a great many surprises. And so, when you look at Saturn, realize that although it is the gem of the sky, in the long run, Titan may be even more significant. Good night.